Hello, everyone, and welcome to my SDC talk on the QUIC protocol. My name is Lars Eggert. I'm a technical director for networking at NetApp. Let's get started. The talk outline is pretty straightforward. I'm going to talk a little bit about what an Internet Transport Protocol is, which is what QUIC is. Some of the current challenges we've been facing with the existing Internet Transport protocols, such as TCP and UDP, SCTP for some degree. Give you an overview of QUIC, highlighting some of the key features that make it different from what we've had in the past with our traditional protocols, and then a brief status. And we're not going to have a discussion, but I'll be around virtually, and you can ask me questions, or you can email me at lars@netapp.com. I should say that a lot of what I'm saying is informed by the standardization the IETF is doing on QUIC. I chair the working group in the IETF, but I'm speaking as an individual and not for the working group or the IETF here. So in a nutshell, QUIC is a new transfer protocol for the internet. It's supposed to be faster than existing transfer protocols. It's supposed to be more secure. It's supposed to be more evolvable in the future. And it's supposed to be for the internet primarily, although there's interest in using QUIC for data centers as well. So what do we mean by fast? It's all about user experience, right? Specifically, since QUIC is initially focusing on web traffic, that is really where the interest lies. Better user experience for the web that you can get with the traditional transport, which is TCP and TLS using HTTP2. But potentially, we're also looking at other content. There's some interest in running SMB, for example, over QUIC. Microsoft has done a prototype here, and obviously better user experience for file system traffic like SMB is also in scope, as might be other applications in the future. Security is very important, specifically for the web and for the internet, right? So QUIC is always encrypted. There's no way to turn off TLS with QUIC anymore. And specifically, QUIC is built on TLS 1.3, which is the latest standard out of the IETF, which has some stronger security properties than previous versions of TLS had. Specifically, it's much more resistant to pervasive monitoring. Evolvability is key, right? One of the problems that we're facing is that while TCP has had a great run as a protocol, it's really hard to evolve TCP forward these days. There's two aspects to that. One is TCP itself has some hard limitations. For example, you can only have 40 bytes in the option space in the TCP packet. Many of those bytes are already taken for options that are basically best current practice at this point. But also, secondly, the network has made assumptions on what TCP traffic looks like and what TCP traffic should behave like. And it's incredibly difficult to change TCP even a little bit if it sort of deviates from what the network expects TCP to be. And the goal of QUIC is to be a transfer protocol. So while the initial focus is on HTTP for the web, the broader intent eventually is to provide a better transport protocol for all applications and all workloads, including, for example, real-time media, or I mentioned file systems, to provide better abstractions, to allow applications to tie closer to the transport functions and therefore get better performance, and to avoid some of the issues that we've learned that TCP has. So in a nutshell, QUIC, you can think of it as UDP, runs on top of UDP. Congestion control, that's what the CC stands for. TLS for security, HTTP as the initial workload, and that sum is QUIC. I'm going to talk a lot more about all of these, but this is sort of the very high-level overview. The other part of the summary, if you don't want to stick around to the end, is my prediction is that so the QUIC RFCs will probably ship towards the end of 2020, maybe first quarter of 2021, depending on how many nits we find now on the home stretch. And the web will move to QUIC first. HTTP 3 is the HTTP version that will run on top of QUIC. It's semantically identical to HTTP 2, which is the version that runs on top of TCP and TLS. But if that's successful and QUIC delivers the promises that people believe it has, then everything else, I think, will move to QUIC sooner or later. So if you're doing anything with HTTP now and you don't have QUIC on your radar, it really needs to be on your radar now, because HTTP will become QUIC-based. But also if you TCP, if you have a workload that runs on TCP now, you probably want to be aware of QUIC and think about whether layering it on top of QUIC might work. And if you're managing networks, right, QUIC will very soon become a very large part of your network, and you should be aware of it. Right, so first section of this talk, let's dive a little bit deeper into what an internet transport is. Stepping back a little bit, this is familiar maybe to some of you from your college days. There's the internet hourglass, which is this is showing the classical version. Steve Deering presented this like almost not quite 30 years ago, but certainly 25 years ago. It's the layers that we all know and love. You have the physical layer on the bottom. You have layer 2 networking there. You have Ethernet on PPP and others. It shows its age here. Then you have layer 3, which is basically IP, the Internet Protocol, which is the narrow waist, right? So, and then on top of it, the hourglass gets wider. Again, you have different transport protocols. You have different application protocols on top of those, and then you have applications at layer 7. And that's sort of inspired by the OSI model, but it's missing a few layers. And this narrow part means that the intent is that IP would be the internetworking protocol that ties all of these very distinct physical and networking layers together into one global internet. And it would then enable lots of applications to run on top of it using different transport protocols. But IP was sort of the common foundation. The young gentleman in this picture is Vint Cerf, who's now at Google, and I hear 2 years overdue to retire now, still going strong. That was from 1994, and he's wearing the nice T-shirt. It's one of the few shots of Vint where he's not wearing a 3-piece suit, saying IP on everything. That was really the model, right? That whatever the underlying link layer was and the physical layer was, it could run IP because IP is very simple. And the role of the transport layer, since this is the transport layer deep dive, is to provide some additional functionality that applications find useful on top of TCP. TCP just gives you packets and it gives you routes. So you can address a packet to another node on the network and it will maybe get there. But it doesn't really provide any other functionality that's useful for applications. That was the role of the transport protocol. For example, unicast or multicast addressing, multiplexing, having different logical transport flows existing at the same time between multiple computers on the network, giving you streams or messages or both, making sure those streams or messages are reliably delivered or not reliably delivered, making sure you don't overrun the network, which is congestion control, or making sure you don't overrun the receiver, which is flow control, and many other things. So those are the things that are provided by transport protocol, specifically oftentimes by TCP now. And on top of that, you can then more easily layer your applications such as SMTP for mail or HTTP or something else. So as I said, this is the classical version of this, this diagram. The more modern version, this is from the 2015 paper, is called the twisted martini glass version of the internet hourglass. And that's because there's no longer IP. There's IPv4, which is the original version that was just called IP in the previous picture. But now there's also IPv6, and both are sort of deployed in parallel. So the hourglass really has these two stems that are sort of, existing at the same time. Underneath, you still have the same stuff you had before, although more and more of it is based on Ethernet. Other link layers and other networking protocols have fallen a little bit out of favor. Maybe now that there's some RDMA stuff that might eventually change again, but at the moment it seems like RDMA is also going Ethernet. And on top, basically, you don't really have that breadth anymore. You have TCP, nothing else exists in terms of a transport protocol. We've not been successful to deploy anything else on the internet, really. And then you have TLS and HTTP, right? So TCP is the majority of the traffic in the transport protocols. HTTP and TLS are de facto part of transport because these days what you're doing is you're deploying a web app. If you're building a new application, you're layering on top of HTTPS specifically for security. And that's what you do. And that's where all the growth is. So the hourglass in some sense has become a lot more simple at the higher layers, but it has this sort of weird twisted martini shape at the network layer. Why? did that happen, right? So there's a few factors that contributed here. One is that transfer protocols are really slow to evolve, especially TCP. It's very, very highly engineered already. There's decades and decades of history in optimizing TCP for the general internet and all of its different network conditions. And it's a fundamentally different protocol problem to evolve it significantly forward, given the constraints we have in terms of header space and everything being in the clear, none of it being authenticated and so on. So that is really, one fundamental problem with TCP. It's really hard to build something that's better than TCP, and so people use TCP because that's where all the engineering is going, and that's where the shared benefit comes. But then also there was a boom of the Middlebox. Middleboxes are sort of this IETF term that describes anything in a network that isn't a switch or a router. So it's firewalls, and intrusion detection systems, and traffic analyzers, and load balancers, and network address translators, and what have you. And these boxes, they're not part of the original architecture of the internet. They were put in the network to solve specific problems, and they never went away. And typically, these boxes are really also never upgraded. And so the consequence is that the network basically has boxes in it that think they know what TCP and other traffic should look like and how it should behave. And as I mentioned before, changing it even a little bit is very difficult, because somewhere some middle box will not like your change to TCP and will decide to drop the traffic or reboot itself or do something that is not very nice. And so those sort of issues are really problematic when it comes to evolving TCP forward. The original motivation for these boxes, was pretty benign. They were put there to help and manage things. They're TCP accelerators to make the workload faster, and firewalls are supposed to protect the hosts behind themselves. But decades down the line, the problem is that the network has this assumption of what is a valid TCP flow, and anything that looks different is going to get dropped or otherwise has a hard time. And then what else has happened is the rise of the web, right? Almost all content moved on top of HTTPS. It's much easier and cheaper to develop for this sort of higher layer, easier platform than it is to build a transfer protocol or an application protocol on top of IP packets. And that's sort of amplified by the rise of mobile on one side and cloud on the other, with their very rapid development cycles, which are enabled by HTTP. And one of the things that HTTP brought with it is this baked-in client-server assumption, because you have a client and you have a server. You have, it's not necessarily a peer-to-peer system. The original internet had no such limitation, but with HTTP, the idea is that there was a client and there's a server. So what are some of these ossifications, some of these limitations that the network has grown over time compared to what the original vision is? So this is a little slide, and the green stuff is how the original internet architecture envisioned things to be, and what's in red on the other side, on the right-hand side, is where we are now, right? So originally, the idea of the internet was that anybody could send a packet to any other node, anywhere, anytime. You put the IP address on that packet, and you send it into the network, and routing would get it there, or it would get dropped. That has changed because of NATs and firewalls, right? Because of, servers typically can't talk to a client unless the client talks to the server first. And this sort of enforced directionality already is quite limiting compared to what we had before. There's also a timeliness aspect here, in the sense that, firewalls and network address translators sort of don't like idleness. They expect there to be a steady flow of packets in both directions, and if there aren't, then they will drop the binding for that flow, and they will no longer forward traffic. So you have to basically keep that alive in order to make your application work. The original vision that there would be many protocols on top of IP. At the moment, the firewall situation is that anything gets dropped that isn't TCP or UDP. For QUIC, that means we can't evolve forward TCP anymore. So we're stuck with the layer on top of UDP just to get through firewalls. End-to-end addressing, meaning what the address that I put on the network, the network doesn't do anything with other than look at it to route. Now the network is rewriting addresses and ports as it sees fit. IP options were meant to be a way to extend IP, They are a great option now if you want to get your packets dropped, because firewalls do not like IP options. So you cannot use them basically on the internet anymore. More broadly, bits were supposed to have meaning inside one of these layers of the hourglass, versus a view where we are now, where boxes in the network think they can or should touch and understand bits, anywhere in the packet, really, from the network header to the application header. Network is supposed to be stateless, right? It's no longer, hasn't been for a long time. The network assumes that it can track entire connections, and it gets very upset when it can't. And then, data is supposed to have meaning. User data was supposed to have meaning only to the applications, but networks are rewriting or inserting payload data all the time, which causes problems. Right, some of the challenges that TCP is facing in some more detail. So it's not aging well. I mentioned this before. We're hitting some hard limits. For example, the option space in the TCP header can only be 40 bytes. And a lot of them are already taken for like selecting acknowledgements, timestamps, window scale, maximum segment size, and so on. We've done some extensions to TCP, such as multipath TCP or TCP fast open. Multipath TCP needs 12 more bytes out of that option space, and fast open needs sort of 6 to 18 bytes. So there's not a lot of space left. And it's a hard limit. We've tried to come up with clever ways to extend that space. Everything has failed in deployment sooner or later. Multipath TCP was incredibly difficult, not because it's a complicated protocol. It's actually not that complicated. But it needs to look like plain old TCP, because otherwise it gets dropped. So a lot of the engineering that we needed to put into the design of multipath TCP wasn't on getting the multipath part working. It was getting the packets through the network. And TCP is already very complicated, and needing to go through complications like that just for deployment's sake is not a great situation to be in. TCP stacks have very slow upgrade cycles, or had very slow upgrade cycles. Basically, you need to upgrade your kernel, right? And while this is getting easier and easier on consumer operating systems and mobile phones and so on, it's still kind of a big deal on servers. It's pretty invasive. You have to reboot. It's not so bad if you're running it natively in the cloud and you have the ability to shift your load, but for sort of more traditional style designs, a reboot is really something that is pretty high risk and invasive. And so upgrading your TCP stack very frequently, or rebooting the kernel very frequently, isn't sort of a great proposition. And TCP headers and IP headers, for that matter, are not encrypted or even authenticated. That's just what the design of IP was. So the network is free to rewrite it, and the end host can't really do anything about it. IPsec was supposed to fix this, but IPsec had its own set of deployment and management issues. And so that's where we are. The network headers are basically in the clear, which is not great. They leak metadata to make you trackable. QUIC is supposed to fix that. And Middleboxes, I mentioned them before. They meddle with traffic, and this slide has one of some graphs from one of the earlier papers on a helpful Middlebox that tried to accelerate TCP. It does that by spreading the end-to-end control loop there. That might have a really long RTT into 3 control loops that have shorter RTTs, and the control loop in the middle specifically that goes over the wider area network is handled by an accelerated TCP of some sort and has better response time. And in the packet secret diagrams, they show you that you can gain some latency, you can gain some benefit. So this is the Middleboxes that were put in for benign reasons, to help traffic and to make user experience better. But there's other Middleboxes, right? Specifically, there's some nation states that use Middleboxes to attack end users or services, right? Snowden slides showed like quantum insert, which is a NSA technology for racing the server and redirecting a client connection to a server that's under their control transparently in order to intercept traffic and spy on the user. And China uses the Great Firewall, which I guess most people know about, but there's a sort of other aspect to that called the Great Canon, and there's a great paper if you want to read it from 2015 that talks about how China is injecting JavaScript into sites that are served into the global internet and that make the browser that's rendering that page attack another site on the network on behalf of China, which is a problem, if you will. And so the IETF has, for a long time now, had consensus that pervasive monitoring and obviously also using unsuspecting users as attack tools is an attack on the network, and we should do something about this. And to many of the IETFers, this means we should encrypt as much as possible in order to make wholesale snooping attacks very, very costly. Right, and that brings us to QUIC. These three things that I mentioned really sort of contributed to QUIC being developed at Google. It's now been for like 2 or 3 years in IETF standardization. We're almost done with shipping the first version of the RFCs, but the stuff I'm going to talk about now can still change theoretically, although it's somewhat unlikely how far we are in the game. These slides are stolen from Jana Iyengar, and they sort of motivate why Google originally developed QUIC. And so the proposition for Google is, how do you make the web faster for your users? And there's a stack here going, from the browser through HTTP, TLS, the network protocols, into the physical networks to google.com. And there's a certain latency that's associated with that stack. And that's what you had to start out with. So the first thing that Google did, they attacked this problem from the bottom. They improved the physical network. They built a carrier-grade network themselves, a global backbone, a CDN. And so they were able to carve out quite a bit of latency from the bottom and improve user latency that way. Next thing they did, they launched their own browser. So they attacked this thing from the top, right? Chrome and HTTP2, which were sort of developed, not quite hand in hand, but around the same time, they really improved the computation that the browsers needed to do, and also the HTTP protocol. And that really cut out a whole lot of latency from this equation. So that's pretty good, right? You've gotten, and this is not to scale, obviously, but you've gotten, into a much better place than you were before those two things happened. But what's left, right? The only thing that's left now, the low-hanging fruit now, is the transport and the internet protocol to some degree. So that's what motivated QUIC, right? If you want to squeeze more latency out of this picture, that's the thing you haven't touched yet, and this is now where the low-hanging fruit are. I showed you this slide before, so QUIC came out of a motivation to be faster than what TCP/TLS had in order to squeeze the latency out. We want to have security that's at least as good. It needs to be evolvable. I talked about ossification and how we don't want to be limited by the network in the future, and it needs to be a transport protocol. QUIC's not all that new. I mentioned it originates with Google. It's been deployed between Google services and Chrome since 2014. Google is sort of very shy with publishing numbers, but the last numbers I've seen from them, and they're actually numbers and units on the y-axis. So as of 2017, which is a few years ago now, QUIC was already 35% of all Google egress traffic. So all bytes out of Google globally, 35% of that was QUIC. And that, by some estimates, counts as about 7 to 10% of total internet traffic. So even before this became a standard, right, while it was still proprietary in 2017 and earlier, it was a huge number of bytes on the internet. Now we have every browser and every CDN and every hyperscaler implementing QUIC. And I expect that we go from 10% of internet traffic to maybe 50% of internet traffic in very short order. So it's going to be a big change for the network. QUIC in a stack looks, as you might expect. On the left, you have the typical IP TCP, then TLS, then HTTP2 stack. With QUIC, we're running on top of UDP. We are incorporating TLS 1.3 into QUIC. So we're using it to derive keys for the data exchange, but we're carrying the messages to derive the keys over QUIC itself. So it's a little bit sort of an embrace and swallow kind of motion we did with TLS 1.3. And on top of that, we have HTTP3, which is the new HTTP over QUIC. That is how it's going to look like. There's going to be other applications that will want to run over QUIC. Many of them will run actually over HTTP3 and might not even know that they're running on top of QUIC if they're web apps or RESTful APIs. But some might want to layer directly on QUIC without HTTP. in the middle. And I think that is what, for example, Microsoft is doing with their SMB over QUIC prototype. And I guess as other protocols will want to not necessarily eat the overheads of HTTP if they don't have to. So for the IETF working group, though, that is our initial target, and that's what motivated a lot of the designs, to carry HTTP well and make it faster. Why are we using UDP? I mentioned TCP is hard to evolve. It's sort of the common theme of this talk. Other protocols like SDTP, which theoretically are an interesting alternative. They offer some of the same features as QUIC does, but they're basically blocked by Middleboxes. SDTP is really hard to get through the network, specifically the wide area network. And so UDP is really all we have left that is sort of acceptable to Middleboxes. And that's not without problems already, right? Many of the boxes in the network sort of seem to believe that UDP is used only for DNS. And so they have some weird assumptions about what that means. Like, DNS traffic is typically, we used to be, query packet out, reply packet in, maybe a few reply packets, but not more than that. So you have really short binding timeouts, and you could, otherwise treat it quite differently from TCP. And UDP performance when it comes to operating systems hasn't really been a very important thing to focus on. And so there's a lot of issues that are related to the UDP data path in Linux that have been fixed now thanks to QUIC, but also like hardware offload at the moment for UDP-based traffic like QUIC is still a little bit of a question mark. That'll, I guess, change in the short to midterm when NIC vendors realize that there's a market here for having optimized NICs that support better offloading. The other nice thing with UDP is it has benefits, right? So you can deploy your protocol because it just speaks UDP packets. You can deploy it in user space. You do not need to implement it in kernel space. So all these problems that I mentioned before with TCP being limited by how often kernels get upgraded, it's all gone. Whenever you ship a new app, you can ship a new QUIC library with it, and you don't need to touch the kernel, frankly, ever, which is great, right? And you can offer alternative transport types very easily. So, partial reliability can be an upgrade of your QUIC library rather than a kernel upgrade. So UDP has some downsides, but also a lot of benefits. But basically, we have no choice. We have to use it. It's the only thing that'll go through the internet that we have today. Why do we want congestion control? That is, I guess, not really an important thing that I need to explain. Picture is, it's not a parking lot, it's apparently a highway in China during the rush hour. Clearly, congestion control matters here. It also matters on the internet. It's basically an absolute requirement for operation, not over the internet, but also the data center networks. Without congestion control, your application is not going to perform the way you believe it should. And for QUIC, what we're doing, we're stealing what we have done for TCP and we're applying it to QUIC. So we're not innovating a lot here at the moment. We're just taking what works and using it for QUIC, and we're going to improve on it later. As a consequence, QUIC needs some concepts that are familiar from TCP. We need segment numbers or packet numbers in QUIC. We need some sort of acknowledgements that tells the sender that packets got received. We need to estimate around trip time and so on. So all these things are there in QUIC in a form that's very similar to what we have with TCP. I think there will be some innovation here in the future because with QUIC, you can actually change the feedback you're exchanging between sender and receiver or receiver and sender much more freely than with TCP, which has all these problems of not enough header space and the network making assumptions about what should be in that packet. So I think there will be new work in this space, but at the moment, we're just stealing TCP's congestion control for QUIC. Why do we use transport layer security, right? So end-to-end security is critical for the internet. We need to protect the users. We need to prevent the network from ossification. That means we're using encryption for two purposes. Protecting the users is the Snowden argument of why we want encryption. But evolvability argument is sort of new, right? The network has shown that it grows functionality that tries to understand what traffic means, even though you tell it in the protocol spec that you should not do that. And so if the network can't be trusted with keeping its eyes and fingers, frankly, off packet header parts that it shouldn't see or touch, we need to encrypt those. So the network can't see those parts anymore and it can't change them. And that's what we're doing here. So we're basically encrypting almost all the metadata that the TCP header carried in the clear so that the network can't see it. So for example, acknowledgements in QUIC are encrypted. Network can't tell which packets got received and which ones didn't. So this use of encryption to prevent ossification, I think, is an underestimated factor of QUIC and why we're doing this. TLS is very widely used. It's basically, if you are looking at crypto, the first thing that everybody tells you is don't do your own. We don't do our own. We use TLS. We benefit from all the academic and standardization and engineering that goes into TLS stacks. And we obviously, are looking to further gain from TLS improvements like encrypted client hello and so on in the future. We don't want custom security too much to get wrong, too complex. TLS already had some issues in the past, but TLS 1.3 is much simpler, much smaller protocol. It should always be called TLS 2, frankly. It's a very solid base to base our security on. And we're benefiting from new TLS features, like zero RTT handshakes, which were incorporated into TLS. Originally was inspired what QUIC crypto did for Google QUIC. And one of the benefits here is that TLS 1.3.0 RTT compared to the usual TLS 1.2 handshake, you're saving a lot of latency, which is what web apps and other workloads like. Why are we focusing on HTTP? That's where the impact is, frankly. I mentioned before, thanks to the cloud and thanks to mobile, most everything has moved to HTTP. That's where the growth is. And so the industry is incredibly interested in improving user experience for HTTP and improving security of HTTP. There's rapid upgrade cycles for browser servers and CDNs. Those things are very easy to upgrade now, which means we can deploy and update QUIC very quickly, which is nice. We don't need to do it in the kernel. And I think that many other apps will follow. On the bottom, there's a graph that shows some amount of dollar revenue that various e-commerce and other sites gain or lose when latency goes up or down. So there's a lot of money that is sort of very proportionally related to how good the user experience of a site is. So we do HTTP because that's where the initial impact is. I fully expect that what works for HTTP will also work for other workloads. And so there will be a general trend to want to run on top of QUIC. Right. Maybe some highlights of QUIC. QUIC is too complex to really cover it all, but I want to sort of show you some things that are maybe new compared to TCP and are interesting. If you are interested in learning more about QUIC, the RFCs are actually quite readable. There's a few good blog posts, specifically Cloudflare and Fastly have done some very nice blogs on various aspects of QUIC, so you can Google those and find them. This is sort of just scratching the surface a little bit. So I mentioned before that TCP carries a lot of data in the clear in its header, and with QUIC we wanted to sort of really minimize this because we want to prevent ossification and we want to increase user privacy on the network. So QUIC has two types of headers, the long header and a short header. The long header is only used during the QUIC connection establishment, during the handshake, and the short header is then used later during the connection for the bulk of the connection. The top diagram here shows you the long header. It's a little bit longer than the short header, which is on the bottom, hence the name. But with QUIC, the network sees in the clear really only the packet type, meaning is this a short header or a long header? The QUIC version, which is only in the long headers during the handshake, short header packets have no version anymore. You see a destination SID, which is short for connection identification, connection ID, and a packet number. The packet number is obfuscated. So there's two steps here where we are authenticating all that information. So nothing is modifiable by the network, but we're also applying a second obfuscation step for some of that data to make it very hard for Middleboxes to track it. It's still possible if they want to spend the computational overhead, but it's quite difficult. And if you compare that to TCP, that's very minimal because with TCP, all the acknowledgement numbers, all the ECN information, the timestamps, the windows and the scale factors, all of that is in the clear. And it's all unauthenticated. So with QUIC, while some of those things are visible to the network can't change anything, which is good for our purposes. QUIC is version negotiation. So the version field in QUIC is 32 bits, which is quite long compared to like IP as an 8-bit version field, and TCP, frankly, as 0. So there's not really a possibility to negotiate a new version with TCP anymore. What that means is we don't really need to like be frugal with allocating versions. We're not going to run out. That means that it's very easy to rapidly deploy new versions, and we can allow vendor proprietary versions very easily too. The graph on the right is done by some folks in Aachen who've been sort of monitoring the deployment of QUIC on the network for a few years now, and the different lines that are shown there are different colors for different versions of Google QUIC. And you can basically see that every like 3 to 6 months during those years, which are a little bit in the past now, Google has basically completely pivoted their Chrome and server-side QUIC deployments to newer versions. And this is something that isn't really possible with TCP, but it's very possible with QUIC. And I fully expect that others that are deploying QUIC now will do the same thing. There's very few things in QUIC that can't change from one version to the other. We call those the protocol invariants. And it's really only those 4 that are listed, there's 3 that are listed here, right? So basically the location and the length of the connection identifier in the long header packets need to be fixed, because otherwise you can't really do version negotiation. And the location and length of the SID in the short header, if it carries a SID, needs to be there. And we need to standardize a version negotiation response from the server. So if the client tries to speak a version that the server don't understand, there needs to be a standard way that's invariant of the QUIC version to tell the client, I don't speak what you're trying to talk to. And everything else, more or less, is changeable between QUIC versions. So it's quite possible to dramatically rev QUIC as a protocol, but keep the handshake, the version negotiation handshake the same, which is great. So it means we really hope that we have long-term evolvability of QUIC because of this. One little nit here is that term that we increase the unused code points. What that means is that what we found with TCP is that we've always said, you know, these bits are reserved in the specification. We said these bits in the header, for example, they're reserved, and the sender should set them to 0, for example, and the receiver must ignore them. What happens is that Middleboxes basically said, okay, if those bits are not 0, I'm going to drop that packet. And so while we reserve those bits, we could never like unreserve them and use them for anything, because Middleboxes would, you know, freak out. And therefore with QUIC, we're saying, you know, these bits are reserved and the sender must randomize them. And therefore we're hoping that that applies degrees to those code points, so that when we are actually going to use them for something that isn't like transmit random bits, the network will let them through. QUIC has 2 different handshake types. Those go back to the TLS handshakes I mentioned before. One is called a 1 RTT handshake and a 0 RTT handshake. What that means is that when a client and a server talk to each other for the very first time, the handshake is a few exchanges longer, because they need to like establish some initial ground trust. And once that has happened, the server can issue a ticket to the client, which the client can use in the future when it wants to open another connection to that same server. And because the client presents this ticket that the server has issued and it trusts, and you can verify it obviously cryptographically where it should, that means that the server can then bypass a bunch of the steps in the handshake and respond with payload data to the client faster. And it's a huge win in latency for many cases, specifically for sort of transactional protocols that have very short exchanges of data. So with HTTPS, meaning TLS 1.2 over TCP, you needed 7 messages to do a handshake until you could exchange application data. And with QUIC 1 RTT or with TCP without HTTP, it's 5, and with QUIC 0 RTT, it's 2. So it really helps a lot. It also helps with other things like NAT rebinding and connection migration, which I'm not going to talk about very much more. And there's some security caveats that the 0 RTT handshake has some limitations about what data it can carry, but in practice, that doesn't really matter much. Everything else in QUIC is really frames. So unlike TCP, which is like the header that has all of the metadata in it, the header in QUIC really doesn't have things like acknowledgements or other metadata about the connection, such as window sizes. Those are carried in frames, and frames can come in any order after the packet header. This is all the frame types that are currently defined in the spec. The two most important ones are the stream frames, which carry payload data, application payload data, and acknowledgement frames, which carry acknowledgement about which packets were received. Most of the other frames are used to negotiate how many parallel streams can be opened within one connection, what the flow control windows on those streams are, and so on, closing the connection and so on. So it's a very extensible protocol, and frame types are 64-bit compressed types. So we can have very, very many frames. Again, we can extend QUIC easily by adding new frame types and negotiate a version that allows that to be carried, and it gives us a lot of evolvability, we hope. I mentioned just now that there's multiple streams, logical streams within one QUIC connection. This is stolen from SCTP, which had the same idea a decade or two ago. So unlike TCP, where a connection carries one byte stream, logical byte stream that's reliably transmitted, within a QUIC connection, you can carry very, very many logical byte streams at the same time. And it's up to the application for how to prioritize those and whether they're reliably transmitted or unreliably transmitted. So congestion control happens at the connection level, similar to TCP. There's also flow control there, and streams also have a flow control mechanism attached to them. So they are basically the thing that carries units of application data. And they can be uni or bidirectional, they can be opened by client or server or flow control. Many of those things might not be generally useful, but they're useful to HTTP, and therefore they were placed in there. And the number of the number of streams that are allowed to be open for QUIC connections negotiated over time using those frames I showed earlier briefly. Right, to wrap the talk up, and as I said, if you have questions about any of this, you can send me email or you can go and look at the blogs that various people have done. I'm going to wrap up with some current status and what the discussion is in QUIC. So QUIC is being standardized in the IETF, which is the Internet Engineering Task Force. All of you probably know about this. Google QUIC was the proprietary version of QUIC that Google had deployed in the past. Is very different from what IETF QUIC is now. We started out with Google QUIC, and then we evolved it forward to the point where everything is really different now. I mean, we replaced Google gQuic crypto with TLS 1.3. We changed the endianness of the protocol. We redefined the handshake. We redefined version negotiation. So even the Google people will happily admit that IETF QUIC is actually a much better protocol than Google QUIC was. It took time. So the estimated delivery date says 2020 September here. This is probably not going to happen. December is more likely. Q1 2021 is most likely. On the plus side, because we standardized this in the open in the IETF, we have over 20 known implementation efforts. Many of them are open source, and many of them are commercial grade. Like Facebook has a implementation that they have already deployed in the Facebook app and on Facebook backends, which is usable by anybody. Microsoft has open sourced their implementation that is running in the Windows kernel and is able to run as a library on Windows and Linux and other platforms. Mozilla has a Rust implementation that runs in Firefox. Fastly has a C implementation. NetApp has a little toy implementation. Cloudflare has one in Rust. Apple has one that's unfortunately proprietary still. So there's a lot of implementations to use if you're interested in doing a proof of concept with QUIC for some workload that we currently aren't looking at. If you want to participate in the standardization, we have a GitHub site, QUIC working group, quickwg.github.io, which is our sort of landing portal. And there's a Slack that is very active, has almost 300 people, which are all the developers from all of these different organizations. that are sort of chatting daily and testing each other's implementation. So send me a message if you would like to participate in any of these, and I'm happy to connect you. We do regular sort of interops between the different client and server implementations, and we sort of track things in a Google Sheet. This is what it looks like. I think this is from a few versions ago. So you can see very many implementations. Servers are on the horizontal axis, clients on the vertical axis. Greener is better and more letters are better. So basically each test is a letter, and if the test succeeds, you enter the corresponding letter into the box that corresponds to the client server pair. And this is how we sort of keep track about what the status is. There's an automation of this now. This is now possible to automatically be generated using Docker images that the individual implementations are providing. And we have a runner that runs on GitHub Actions every couple hours and runs all of this in parallel. And this matrix is therefore no longer manually updated so much, which is great. Right, I mentioned that the IETF is close to shipping QUIC version 1. What comes beyond version 1 is slightly unclear at the moment. My best guess is we're going to see more applications on top of QUIC. I already mentioned that Microsoft has already done a prototype of SMB over QUIC. I think we're going to see other implementations follow suit. For example, NFS at the moment, the IETF file system protocol, is growing support for running on top of TLS. Once it can run on top of TLS, it doesn't really care whether there's TCP underneath or QUIC. So that's an avenue forward. But I also expect other protocols will want to run on top of QUIC. Especially, we see a lot of interest from having real-time traffic go over QUIC. With TCP, I mentioned we have done an extension called multipath TCP, which Apple has deployed, but otherwise it's had a sort of little bit of a tough deployment story. Recently with, I think, kernel 5.8 or 5.9, it's now in Linux, which hopefully gets it more deployment. But multipath use of QUIC, so basically the ability to use multiple paths in the network for one QUIC connection at the same time is something that some people are very interested in, others not so much. So it's a discussion of whether we really want to tackle that. I think we're going to see a whole bunch of performance work on QUIC, optimizing it in terms of congestion control, optimizing it, for example, for satellite deployments, which traditionally relied on some of these Middleboxes that I mentioned before to operate well. I think we're going to see also some offload, NIC offload work here. So that is one area. And then QUIC extensions. We already saw quite a few extensions that are proposed in the IETF. I think we're going to see a whole lot more of those. And maybe there's something that isn't on this slide. So it's pretty opaque at the moment what might happen once QUIC ships and runs probably the majority of the bytes on the internet in a very short time scale. Right. Before I go, because I think I'm running a little bit out of time, how can you participate in all of this? So the QUIC working group in the IETF is open to all. There's no fee for joining or no membership, corporate or otherwise. You join the mailing list, you discuss issues and pull requests on GitHub, you participate in the meetings, which is very easy now since they're not physical anymore. QUICwg.org will get you started. You can also talk to me. And there's a IETF IPR policy, so if you participate in the IETF, there's some things you need to follow in terms of disclosing IPR. The IETF is an organization that's open to all. We meet 3 times a year. The next meetings are probably all not going to happen as planned. They'll all be on Zoom. There's various ways to participate if you're an academic that make it cheap for you to do so. If you're not an academic, you can hope that your corporation will pay for you. And we're on, very much on GitHub. We're one of the sort of most aggressive users of GitHub in the IETF. So pretty much everything that's interesting happens, and it's easy to follow if you're on GitHub anyway for your other open source needs. And that's basically it. Thank you very much. I hope this was interesting to some of you. I know there's some other talks related to QUIC later. I'll be sure to check them out, and I'll hope to see you virtually in the hallways in some form.